All right, bubble sort. We have our good old big O n squared. Selection sort, also big O n squared. Insertion sort, again, the same thing, n squared. Quick sort, big O n squared. And merge sort, it's big O n low again. All right, so if this was our only decision point between our 5 sorts and we're asked to sort some data. Yeah, it's n squared because they're nested loops that in the worst case, they're just chipping away one closer to where we're getting to. Right, one pass on the bubble sort gets us the largest value to the end. Selection sort, one pass on the unsorted set to find the smallest value to get that smallest value to the front. Insertion sort, right? A shift n times that can shift all the way to the beginning. Quick sort if we have bad pivot selection. Then we have lopsided pivots. We're just getting one to either end, chipping away. And merge sort is the only one that actually has the best of the 5, but that's not the one that the library uses. The library does use quick sort, right? So, but just at this level, we would want to use merge sort. But the fact that it wasn't chosen meant there were additional considerations that we had to take a look at. Let's see. Find my sorting section. There we are. Let's see. Got some links here in the pages section that will show us them. We do have selection sorts up here on the top left, insertion sort top right, merge sort on the left side, quick sort right here in the middle, and bubble sort bottom left. Right, so we're not talking about shell sort, comb sort, cocktail sort in this class. Heap sort we'll get to later. Let's slow this down. And I don't need the audio. All right, so different algorithms have different approaches for how they're getting things squared away. So this YouTube video just shows you the red bars, the elements that we're just starting to look at. And we'll go ahead and let it go till we see who's the winner of our first sort at the moment. All right, Quick's doing well, but yeah, it's hard. You never know until you get to the end. See, selection sort's not doing terribly well. Bubble sort, there we go. Quick sort was our winner. All right, so on this set of data, and this video does go through several iterations for different types of data patterns. We can see that the quick sort was quick. It's not sarcastically named, it's not sarcastically, it's not the word I'm looking for, but that's the idea. But merge sort's getting pretty close here. We can see we have 2 lists that are almost merged together. And it's just be a matter of merging those 2 lists together. And that one's done. All right, so merge sort wasn't far behind. And we, in fact, where's my big old cheat sheet? All right, big old cheat sheet. Oh, one sec. All right, we do even have a section here just for sorting. Note, we do have the 3 classifications for our time complexity. We got the best case, average case, and worst case, right? So remember, worst case is the value that we use unless we're saying we're looking at the average case or we're looking at the best case. All right, so first up, quick sort n squared, just like bubble, insertion, and selection. And then we've got our merge sort, which is the same across the board, and log n and log n and log n, because the very first thing the merge sort does is it cuts things in half. So it guarantees the good splitting. But the average case, which tends to be most relevant, you know, is doing theta, not O here. Tends to be more important than the worst case for most scenarios. All right, and quicksort, merge sort being very close together, but merge sort has a memory overhead that's a little bit more significant, which is why the merge sort tends to get pulled out of the picture when we're choosing different sort options. All right, insertion's still trying to work its way there, but 2/3 of the way. See bubble sort and selection sort. Not parties that we want to go to if we're expecting to get our drink orders in time. Insertion sort of our simpler ones, it's definitely got the best performance characteristics for average case, and the best case is really good because if the list is already sorted, it doesn't have far to move anyone at all. It gets really close down to linear time. You can cross-reference the cheat sheet on that one. But there's a, and I forget who created this video, but they have other videos as well, even more sorts going side by side. All right, insertion's done, bubble still bubbling around. Selection's getting faster, right? Because this list that it has to search through gets shorter and shorter as it goes. So it has now completed, but bubble sort, that swap overhead, it's pretty significant. Right? Even it's, you can see it's getting a little bit faster because again, the remaining part of the list that it has to go through does at least shrink over time, but swapping is an expensive operation, right? It takes 3 operations just to move 2 values around. So a lot of overhead as far as time and work is concerned. All right, so the O notation is our quick litmus test for which way we want things to go. And you can see there's different data scenarios for what we're doing here. Quick sort still one out, and merge sort, insertion sort. Right, so still have similar patterns going on. For the data, I think it gets to the worst case, so you can check out the video. Skip along. And see all the various fun things. Right, you can see the worst case scenario, especially for insertion sort when it's already in the reverse order, because everyone has to shift, and bubble sort really suffers because it's got the same thing. Every value is bubbling all the way to the top. Right, so the selection sort is pretty much the same amount of time every time for all the patterns, right? Because it's best case, worst case, average case, it's got the same mechanics to go through. And insertion sort is definitely feeling the pain of the data being in the reverse order. We wouldn't use bubble sort. We use bubble sort as our first sort because it's the simplest algorithm. And once you start learning one pattern, then you can start building from that pattern to see other patterns of working with data. All right, so yes, it's one of those elementary scenarios type thing. All right, so this tool lets you step through and see the various algorithms at work. And it has various sorts on the left-hand side. All right, so the big reason, where's the page? All right, so quick sort is our library sort. On average, we get down to our big O and log n. is typically going to be avoided. Because the memory overhead. Now I forget, since I wasn't doing terribly well last week. Did we get to the code for merge sort? I want to say we didn't. So we do want to look at the merge sort code still, right? Correct me if I'm wrong.
Yes, please.
All right, so let's go pull up our code in the files section, sorting folder, and get down merge sort again. Probably right on my computer. Let's see, we're version 4 or 5 now. Oh, that's right. I did a bunch of housekeeping. It's like it was never here. Okay. All right, our merge sort, one of our recursive algorithms. You can see the very first steps are going to be to divide the array. All right, so we'll take the boundaries that we're going to be working on any individual call into our merge sort, starting off with the entire array. All right, so our sample here, we have 10 elements. So we'll go through the first to last element, sorting the array, and then here's our memory overhead. We have a temporary array that's the same size as the array itself that we're going to go ahead and use to support the operations. So that this is the space complexity for this algorithm is twice that of the array, which is why Quicksort has won out as the library implementation for the C standard library. So coming in, right, left, again, remember we're doing integer math, and make sure put the parentheses here like some of you ran into with the binary search. We do want the addition to happen before the division, otherwise we don't quite get to the middle that we're looking for. So first time through, 0 and 9, we'll have our 0, 9 here, and then 9 divided by 2 is 4, and we'll split, right? So we'll make our first recursive call again, left boundary, the middle, 0 through 4 comes in, right? Gets us to 0 and 2, so like we had on our whiteboard last week, we're going to keep getting this down until we're down to 0 or 1 element for our merge sort. All right, so our base case to our recursion here on line 11, if we get to the point where there is no array or subsection of the array that we need to work on, we're done with our splitting. And then we can toggle over to the right-hand side to get those. All right, so here's where our temporary array is going to be used. There's 2 steps for the data copy, right? Left side and right side. And we're doing a little bit of math on the right-hand side here to avoid some boundary checking in the code. So copying the left-hand side is just straight copy into the temporary at an index in the array somewhere I and I with an offset of 1, so it's just a straight copy over. But on the right-hand side, we're going to do a little bit of a flip. We're doing that flip of the map with some math here to calculate a reverse. So what's going to happen? Let's say if we have 1, 2, and 3 as the left-hand side, the left values, and we have halves that we want to merge together. I don't know, was that just a glitch on you? Or was it glitch? Okay. Good old Cox internet over here. Okay, so let me rewind a moment or two and repeat. So if we have the values 1, 2, 3 on the left-hand side, and we have the values 4, 5, 6 on the right-hand side, right, our 2 sorted lists that we want to go ahead and merge together. When we copy it into the temporary array, the right-hand side will be flipped to be 6, 5, 4. left half and right half, or the entire subsection of the array that we want to merge together. So the reason why we do this is as we're pulling values, right, since all our small values are on the left list, we'll pull 1, compare that to 4, pull 2, compare that to 4, pull 3, compare that to 4, and then the left-hand side is actually going to cross over into the right-hand side, and we'll be comparing 6 versus 4. So we'll pull 4, 6 versus 5, we'll pull 5, and then 6 versus itself. And it saves us from having to go check, did we go below the left-hand side or did we go above the right-hand side when we're doing the merge operation. So it's a micro optimization. Since we have to copy into the temp array anyways, over here on line 30, they just add a little math here to save us a bunch of extra testing for the merge step. All right, so what we're doing is I represents the left list and J represents the right list. Just look at the front of each list. Whoever's the smaller, we'll go ahead and pull that from our temporary array. Increment the left if we pull from the left, or pull from the temporary on the right-hand side, and we'll decrement the right if we pull from the right as we copy that back into the source array. And if you've forgotten, yes, go ahead.
Can you repeat that one more time? About pulling from the temporary array on the right and the left?
Yeah, in fact, we'll do it over here with the alternative code. Right, so instead of using our conditional operator or ternary operator, this is lines 43 through 46, the logical equivalent if statement to line 37. So we just compare the front of each of our two sorted arrays. If the left-hand side is lesser, we'll go ahead and pull from the temp array on the left-hand side, and then increment the left-hand side pointer into our source array. And if it's not less than, go ahead and pull from the right-hand side with J, and that one moves down. So I and J are just moving towards each other, which forces our boundaries to be good. Except most, if we do cross over from left to right or from right to left, we're always looking at a valid value from one of the two lists. All right, so another reminder about the preprocessor directives. If you want, when you run this code locally, if you want it to show temporary output, just go ahead and add a pound define to the top of your code file, and it will go ahead and print all that good stuff like we have here. All right, so let's see if I have the right project open here. Okay. Let's do a little stepping through. CRAs in action. Let's see if it wants to build. It says I have 22 errors. Oh, that's right. I had a bunch of comments in there I added, didn't I? Let's go ahead and get rid of my bugs. Try that again. All right, so merging. Step one, we need to go ahead and divide. As we keep on dividing, we'll go ahead and conquer this until eventually. All right, so we're getting close. Left is 0, right is 1. So calls a merge sort, and then we have 0 and 0. So this last call got us to the point where we're looking at the very first element in our array. All right, we have 12 at index 0. One and only element. So we can go ahead and come back out. Now that we have the left list identified, element 0, do the same thing on the right-hand side. We have left is 1, right is 1. And we now have 2 lists. Now we can start merging. All right, so copying one element into the temp array, it's not a whole lot to do. And then copying one element in the temp array, not a whole lot to do with just there being one element. So we have two one element lists. Let's see, so we have I for the left-hand side and J for the right-hand side. All right, compare 12 to 71. Whoever's smaller, we'll copy over. All right, so we'll get array. So, okay. All right, so we're copying back into the array on top of whatever the previous contents were. Since we have the data in the temp array, we're good to do so. So it's copying 12 back on top of itself with the data set that we have. And now both the left-hand side and the right-hand side, see we crossed over. Both looking at 71, and we're just going to grab 71, copy it over into the array. So since 12 and 71 were already in relative order, not much to do, but that is now a longer sorted subarray. And we can move out till it gets bigger. In the process, we'll repeat on the larger sets. Is the recursion making some sense here? All right, the recursive part is just getting us down into our sorted subarrays that are one long to start. Merge those two ones to twos, then go get another pair of ones, merge that pair of ones to a 2. That gives us a pair of 2s that we can start merging together. And depending on how even the array is, this one's got 10, so it'll be a little bit, a 2 and a 3 might get merged together depending on how things get split. Everyone's good for the moment. Okay, let's circle back to the quick sort. Any questions on our 3 pivot selection strategies? Remember, the pivot is the value that we're going to be building our 2 subsets. Values smaller than the pivot to one side, values greater than the pivot to the other. And again, we're recursive, except this time with quicksort, we're doing the recursion at the end of things. There's only key differences between a merge sort and a quicksort. The merge sort's doing this recursive step to the beginning to evenly divide as evenly as possible, right? Because you can't evenly divide an odd length array. We can get pretty close sometimes. Does everyone recall what our 3 pivot selections are? Anybody remember what day of the week it is? I've forgotten 3 times already. I think I know what the month is. Have I lost my connection? Am I talking to myself? Let's.
No, you're good.
There we are. Okay.
Is it center, front, and back?
Yeah. So we have the middle one. Just grab the middle element on the assumption in case the data is already sorted or partly sorted. It's a good value for a median. The first value, which is the naive approach, because if it's an already sorted list, we have problems because that's going to give us our worst case scenario. And median of 3. So the median of 3 is when we take the first, the last, and the middle element and find which is the median of those 3 numbers, right? Which means we take those 3 numbers, basically sort those 3 numbers, and then take the middle value of those 3, which is the median, because that divides, puts one value on either side. That's one's lower and one's higher. That sound familiar?
Yeah.
Yep.
Thank you. All right. Which line is our base case for this quick sort? When will we stop making recursive calls? Yep, line 43. All right, being right. Right, there's actually two base cases in this one. But you've got the right idea. When we're getting down to the point where we see that the work is done, we can stop making our recursive calls. Okay, so be careful. This one's a little bit trickier to identify the base case. But 43 is the right idea. But 73 and 79 are where our base cases are for this one. Yeah, and that's another way to represent the base case is when the lists get to a certain point in size. Okay. Let's see. While we're on the subject of recursion, any other questions about that at the moment? As we start rolling into trees, it's going to become more prevalent in our various algorithms for working through our structures.
Yeah, so when you're testing us on this, will we need to know the best case, worst case, average case, and how to find those?
Yes. So if I ask the question, where's my notepad there? Okay, what is the big O of bubble sort? Right, n squared is the big O, but I can also ask the same question, right, in the best case, right, assuming we have our test, right, so we can write a big O implementation that if it's already sorted, it will do zero swaps. Zero swaps indicates there's no work to be done, and we will be done with our sort. Right, so this is the one that many often get tripped up on. It's the quick sort, because big O quick sort is n squared in the worst case. It's when we change this to average case that our answer also changes down to our n log n. So the O notations are definitely questions we'll ask on the next test for those various sorts. And then other things we can get to, which I'll release the practice test probably before Thursday this week. So you guys can take a look at that, go over that next time. Other ways we can compare our sorts, right? Because at the top level, we have our big O notation, right? It's to be some sort of strange circumstance that we would decide to take an n cubed over an n squared algorithm for whatever our problem is, because n cubed, as we've seen on the charts, they grow really fast. Right? N square is not ideal. N cubed is going to be still further to the left as much as possible. Let's try to stay in the orange range or better when we can. It's not always an option to get into this space, depending on what we're trying to do. Right, this is our first comparison. One of the things I don't think I've pointed out in this chart, you notice that right, this orange range represents the n log n, right? Because we can have multiple n log n algorithms to solve our problem, but the overhead that exists between the algorithms will be our next deciding factor. Right? If something's persistently staying well above this line, or something's persistently staying well below this line with our representative data, then we want to go with the one that consistently performs better, right? So the ultimate idea is we want the algorithm that's going to get the job done with the fewest resources. Okay, 1 second. Take a look at something. Why is log n and constant log n and constant r on the same? They're not quite the same line. They're just really, really, really close. Constant is literally a horizontal line, and log n is a line that grows a little bit slower. Remember the scale on that image? It's not 1-for-1. Right, a 1-for-1 scale would have n be the diagonal. So the scale is tilted, so that's why it looks like log n and constant are so close together. But log n does grow really, really, really slowly. Not quite as slow as constant, because constant has no growth, but it is still pretty slow. Let's see. Right. Right, so let me come back to that page, right? So here's, right, linear. If this was a 1-to-1 scale, linear would be where this color between orange and reddish, whatever that color is, that would be a 1-to-1 scale. So the scale of this chart 1-to-1, it is what, like 10-to-1 or something like that. So it makes it look like these are the same. So really, 1 is basically the black line at the bottom. You see that the horizontal axis is twice as thick as the vertical axis. It's because constant is one of the lines. And then the log n is so close there that it's pretty much been blended into the line. But yeah, that's because of the scale. So it's not quite the same line, right? Log base 10, as I have here, 100 still 2. So you have to get all the way to 100 before it pops up to a 2 type thing. How do you, I'm not quite following. How do you even calculate n log n? What do you mean by calculate n log n? Yeah, it's just n times n log n. Right, so if n was 100, 100 times, as they have it here, base 10, 100 would be 2. So the whole thing would be 200. Okay. Yeah, for base 10, basically number of digits minus 1 is pretty much get you about what the log would be. Okay. Yeah, for base 10, it depends on the base. All right, so if we don't have other questions at the moment for sorting multidimensional arrays is our next item. The root folder. Sure. I mean, the link to it is on the syllabus. All right, so the whiteboards is our root folder. Okay. Multidimensional arrays are an abstraction of single dimensional RAM space, RAM memory. All right, so if we define a matrix, that matrix needs to have the elements, if I can type, mapped to their respective locations in memory. And there are two different ways that we can represent the mapping of those elements. Let's go back and get a foundation on single dimensional arrays first. We got there 7. All right, so a single dimensional array. There is only one way to do this because it's just one dimension, just maps straight across. Right, index 0 is our first element, and index 1 being our next, and so on as we go through our elements. And the way that memory is allocated for this, each element in the array is right after the element previous to it. Right? With our arrays, we are contiguously allocated. And let's get the memory address. All right, so if our memory address, all right, so if we ask out, all right, if we did a C out, address of array type thing, and if that says 100, value of our pointer, that is array, holds a memory address 100, and we'll keep these in base 10 for the moment. At index 0, we have the value 1, our first element in the array. Assuming these are 4-byte integers, and it's assumption there. Assuming 4-byte ints, all right, 32-bit system. Each element that is in the array is going to be just 4 bytes greater than its predecessor. So we can just keep on adding 4 bytes to the memory addresses to see where things are. All right, this contiguous allocation is what is supporting our random access. Contiguous allocation of our memory space for the array is what allows random access. We can get to array sub 0, same number of operations as we can get to array sub 5, all right, any arbitrary position. All right, so our indexing operator, what we're doing here is we're taking base address, which is the value of the array variable, 100 in this example. Then we look at the value in the square brackets. to use as an offset. And we have 5 in this sample here, or this is actually, we'll just do 0. And then we'll do 5 as an offset times the size of an element to get to the location memory where the given element is. All right, so array sub 0, it's going to be at our base address of 100 plus offsetting by 0 elements, since it's the first element, times 4 bytes per element. And it gives us the memory address. 100 is the memory address of the first element. And it's the same calculation for every other element. So if we look at 100 plus 1 times 4 takes us to 104. If we skip along to 5 times 4 skips along to 120, which we can cross-check up here in our chart, our table. Well, the value, Rex, remember, array is a reference type variable. Reference type variables hold on to memory addresses. So the value of the variable is a memory address, which in this example here is just 100. And then the value, whether it's a variable or a literal, is plugged into the formula here. And that tells us where the location memory, the 6th element, is in our array. All right, so if we had, yeah. All right, so it doesn't matter if we're doing instar array and we're newing it up to give us 10 elements on the heap, or we're just doing our stack based. All right, 10 elements on the stack. All right, both are still references, which holds memory address. It's the base address from which we get to any element in the array. All right, so let's add a second row. Let's see how this is going to work. All right, so here we have row 0 and its corresponding memory address, and then we have row 1. Let's see if I can get everything to squeeze. All right. So let's shrink this down a little bit. Definitely have enough space now. Okay. So if we define the matrix, 2 rows with 5 columns. All right, this is going to give us indices 0, 0 to 1, 4. Through 1, 4. Right, so we have 0, 0, 0 here, and then we'd have 1, 0 here as soon as we get some data points in here. And then we'll have our corresponding memory addresses after that. So let's actually split this up. Do this as 2 charts. And we'll have the data in one. And memory addresses in the other. As we do this. Okay, so assuming our base X is still 100, there's 2 ways that we can lay the data out. The more common way is to do row major order. We'll go ahead and fill row by row with our data points. And there's also column major order, which will fill column by column with our data points, which is a less common style. So with row major, elements will flow like they were the one-dimensional array. Down the row. So if we had, so we had our data points 1, 4, 7, 9 in our definition, then it would be laid out here 1, 4, 6, 7, 9. So let's define matrix type thing. 1, 4, 6, 7, 9 is our first row, and 15, 3, 19, 22, and 44 as our second row. All right, so if this was just the one-dimensional array, we'd have one row, row 0, 1, 4, 6, 7, and 9. As soon as we add 5 more elements as a second row, it comes along here as if it was just one-dimensional array itself, 15, 3, 19, 22, 44, just like we had up above. The memory addresses are going to still follow the same pattern. All right, so our row major order, base address, the very first element in our matrix, our array. Assuming it's at memory address 100, each up will be 4 bytes after. And then we'll just wrap around. When we get down to the next row, it's 4 bytes greater than its previous element. Right, so the last element in the first row was at 116. So we're taking bytes 1, 16, 17, 18, and 19. Right, 4 bytes for a variable. The very first element in the second row will be at 120, and the pattern continues, and we'll just roll through. So we have 10 element array, still takes the same amount of size. We're looking at 40 bytes, 10 4 element bytes. Memory address is 100 through 136, taking up bytes 100 through 139. Let's see, question. So we treat it like the first row continues in terms of calculations. Yeah, because that's what we're doing, right? So we're mapping this matrix, right? So if we're looking at the actual RAM, right, the values in RAM are just going to be 1, 4, 6, 7, 9, 15, 3, 19, 22, 44, right? So basically, that's the whole objective here, is how we're going to map this multidimensional array onto a physical space, right? Because RAM is basically effectively one massive one-dimensional array, right? If the operating system has given us 100 megabytes to play with for our application, and we decide to work with any area of the array, it's just memory address 0, we'll say, to memory address 100 megabyte type thing. Yes, Omar, the first table is the values, and the second one is the addresses. So values and addresses. Right, so this is our RAM for our row major matrix, and it looks pretty much the same as it would for one dimensional. So if we compare to our one dimensional for a 1D array, right, which whatever the values were, just comma this one. All right, 10 elements for a matrix, 10 elements for the array, each of which takes 40 bytes. It's just the way that we're indexing into the matrix, allowing us to index by row and column to allow us to abstract the data in a sense that makes more sense. Or if we're doing a checkers board, we could implement a checkers as a one-dimensional array of 40 squares or 80 squares if we want to include the empty spaces, or to keep life simpler from the application development side, we can create it as a two-dimensional array, right? So if I'd known about two-dimensional arrays when I took Visual Basic a long time ago, I would have done it that way. But since I didn't know about two-dimensional arrays, I actually wrote my chess program, checkers, one or the other. It's probably checkers first. Checkers program with a one-dimensional array. So I was just doing tests. If my value was between 8 and 15, I was in the second row. If my value was between 16 and 24 type thing, I was in the third row, right? So I did the two-dimensional matrix as a programming abstraction in my own code because I didn't know about multidimensional arrays at that point in time. Can you rephrase your question, Mohammed? How do I get row 1 for values? The values are here, and if I actually just initialized it, let's in a row matrix system, there's definitely a difference because the math's a little bit different because we were talking about two values that we need to use to do the calculation. But where it ends up, the sixth element will be the same place. Whether it's a 2x10 or a 3x14, the sixth element is going to be 24 bytes offset from the base address if we're talking about 4-byte variables. It's just how we calculate to get to the sixth element is a little bit different depending on if it's a 2x10 or 4x5, because in one case we are going past rows and we're not. So let's get to the math before we switch over to the code. Well, take a break, then we'll switch over to the code. All right, so like we had with one-dimensional arrays, doing is calculating how many elements are already allocated before the element in question. Right, so when we have array 5, or just say array X elements have been allocated before X. Right, so 0 in the case of 0, or 5 in the case of 5, as it is the sixth element. Right, and this is pretty much the whole reason why arrays are 0 based. First element is indexed 0 because of the math behind how we're actually getting to locations in memory with indexing. Oh, how do you get, those are just arbitrary values, right? So set of arbitrary values. All right, so with there being 2 dimensions, what we're going to do is look at how many rows have already been allocated, and then how many elements in the row in question have been allocated to determine what the memory address is. Right, so we have our matrix defined as 2, 5. All right, so we have 10 elements. Assuming we're 4-byte elements in size, and the base address is 100 again. Let's just make it 4. No, I'll do 100 consistency for a moment. All right, so the matrix 0, 0. All right, we're going to have our base address plus 0 rows times size of the row plus 0 elements times size of an element. Let's see. Be on one line. All right, so that is 100 plus 0 times the size of a row. All right, a row is 5 elements. Right, 2 by 5, 2 rows, 5 wide, just 5 elements times 4 bytes per element plus 0 elements times 4 bytes per element. All right, which is 100 plus 0 times 20 plus 0 times 4, which gives us 100. Right, same as before, the fact that there's 2 dimensions does not change where the first element is, still in the same location. So if we look for the second element in the array, base address is going to be the same for this given, still not gone past a row, but we have gone past one element to give us position 104. If we go for 1, 0, 1, 0 means we've passed a row. 5 elements have already been allocated before us, and 0 elements have been allocated in the second row. Going down to the last possible, 1, 4, 100, 1 row, which gives us 20 bytes, plus 4 elements, giving us down to 136, highest possible memory address. All right, remember that multiplication works. The other way to do this is alternatively do 100, right, plus previous elements times element size. So it's the same math, just undistributing it type thing. So 100 plus 0 times 5 plus 1 times 4. All right, so we have 0 rows, 1 element. All right, math's the same, 104. All right, copy, paste, change values. All right, so if we want 1, 0 and 1, 4, just plugging in numbers here. Those become the givens. This becomes the 4. So let's add some color coding. Okay, no. Map the colors to where they are in the formula. One of those places where non-digital is the way to go. I'll get to your question in a second after I finish coloring this up. And come over here. All right, and then we have the given up here that plugs in to all these 4s. So many 4s. Halfway there. And then the 5 is our last given. Purple, good enough. Purple, purple, purple. All right, so it's just a formula. All right, the same color's gonna play over here. All right, the base address, right? That one I think stands out. I believe that one's black. Okay, so no, Mohammed, the data values are just arbitrary data values, right? Because the array of integers can hold any integer value. So is it 4 bytes because an int long float? Yes. The number of bytes is based off the data type, and 4 bytes is the most common size. So we use 4 bytes. So it's whatever the element type is. Right, it's determined by the data type of the array. All right, so if we were using chars or W chars, it'd be 1 or 2 bytes per element. Yeah, so 1 through 8 would be the most common values seen in an array. 1 fairly common because of strings, right? So many ASCII strings, and then 4 being common because ints are a very most common numeric type. Let's see, let me fix my numbers here. 120, 136, thank you. Copy, good old copy paste. Yeah, so right, these formulas are the same. It's just right because there's the size of row, size of in the size of row calculation. There's a size of element in there as well, so you can just right. This is the distributed form. This one's the non-distributed form. It's the same formula. The math is the same. Let's see. Okay, allocating arrays, multidimensional arrays. Let's see. Refuse to connect such because I'm in a frame. Man, I don't know what's going on with this site. That's kind of a bummer. A bunch of links. Ooh, I think we can cut that out. Let's cut a little bit more. All right. Right, so row major, column major. Right, row major being the same way as words, right? Words in English are a row major pattern, right? Whereas you have some languages like Japanese, Japanese is a column major. I think they go right to left as well. Is that right? I forget. It's somewhat arbitrary which way you go. And when things are arbitrary, you tend to default to what's more similar to other patterns that you already have. And since row major order is how alphabetical characters are, right? Words and characters and words are lined out that way. That's why row major order tends to be the more popular. Yes, we're almost at coffee time. So ij is base address plus byte size times I times or columns plus j. I plus j. Yes, Chloe, that is the formula. Let's see. It's definitely one of the areas we're getting into the math side of things. All right, so feel free to avoid things when it gets a little bit too math heavy, because definitely blah. Totally like to try to stick to the algorithm side and avoid the math side, but a few other websites for you to check out. It's an old show now, but 24 actually had an episode on this very topic, row major versus column major, because they had one system that stored the data at column major and they needed to feed it into a system that stores row major. And you have to do a matrix transformation to do that, right? Which is on the fun math side, which I'll leave to other classes in order for these systems to understand each other, right? Because the data format is incredibly important. If you have the memory address that stores an integer data and then try to treat it as a float, the computer is just going to give you bad results because the internal structure of an int is vastly different than the internal structure of a float, even though they're both 4 bytes in size. What? Less and less. Not as many use column major anymore. I believe Wikipedia still has it on who still uses column major. Yes, Fortran, yeah, MATLAB. So I think MATLAB still is column major order. But most programming languages are row major, C, or at least the most popular programming languages, C, C++, Objective-C, C Sharp, Java, all the .NETs, JavaScript, right? It's all row major. So you can run into a system where if you're trying to get a data file that was generated Fortran, yeah, a life vector. Okay. Anyways, all right. Let's go ahead and take 5 minutes and then we can pull up some sample code, show how it's being arranged there. So let's take 5, come back at 20 after. All right, go pull some code files again. Let's see, it should be in linear, if I recall correctly. Where's my arrays? There's my arrays. All right, so like we saw on Wikipedia, we are going to be row major. For however many dimensions we have. Let's see. Tilt to run, try to tilt to run. I guess I need a breakpoint here. Yeah, those are not defined. Where is my output window? There you are. Okay. So here on line 27, we have matrix being defined, 2 rows, 5 columns, and we're using a one-dimensional initialization list. Believe we're still recording. Was it paused when yeah, we're still recording. I see the recording icon. Okay, so we have, that's all good. Double checking is the way to go. 0 through 9 as a single dimensional initialization list. Right, so the first 5 elements end up in the first row, and then the second 5 elements end up in the second row. And we just use a typical for loop, no, pair of for loops, that is, to index into our array. The outer loop being the one for the rows, so I goes from 0 to 2, and the inner loop, j through 5, for each individual row. And if we don't like just 2 dimensions, we could always go 7-dimensional array if we want. Look at our locals. All right, 7-dimensional array, which has, all right, just keep on digging until we eventually get to all our data elements. It's the same pattern. How many elements were allocated before me? All right, so at the first layer, we have rows of 3 elements, a matrix of 2 by 3 elements. Now we've got a cube of 3 by 2 by 3 elements type things. I guess that'd be a cylinder, the square base. And then, right, the pattern just continues on for whatever time, whatever dimension above time is, there's only one of them, and then so on and so forth. Same math applies. Right, the first 3 elements go into the first row, the next 3 elements go into the next row, and then the next 3 elements go into the row that's in the next plane. Right, next row in the next plane, et cetera, and it just keeps on filling them up. Because that's what we have, is just one-dimensional array. So if you look at the memory addresses of these things, all right, this now it's in base 16, so it's in hex address here, but the address of these just continue to ascend as we go up. Right, EC8, then it's D4, triple E, et cetera, et cetera, et cetera. It's still contiguously allocated array. The fact that we've abstracted it into multiple dimensions only gives us a headache, because 2 dimensions is about as far as multidimensional arrays typically go, right? Like the screen of pixels that we're looking at here be represented as a 2-dimensional array. Might be a 3-dimensional array where we have a front buffer and a back buffer. Usually that's just set as 2 2-dimensional arrays, and a pointer points to whichever one it wants to point to for when it actually gets to the draw event to represent the pixels on the screen. Because that's called double buffering, and that's what allows the screen not to flicker as things move around on the screen. They're really old systems, you would get partially drawn artifacts as it had to redraw the data state. Right, column major is the same thing, it's just a different formula. I'm not going to ask you any math questions for column major on the test. Just need that know that column major is the other way that things could be internally stored. But row major is C++, and C++ is what we're using. When's the next exam? So that would be in 2 weeks, if I recall correctly. All right, test 2 will be on October 4th. Yes, so it's in 2 weeks. I'll publish it and the practice so that you can see the dates. These items pop up in the syllabus. But row major ordering is the last area for test 2. So sorting is a big chunk, then recursion, and then the row major order. And double linked lists can make a showing there as well. So any questions at the moment? Okay. Yes, we are going into trees right now. Trees. All right, so trees are a non-linear data structure. Generally described from a top-down visual where the root of the tree is at the top and the branches go down. So it looks more like the root system of a tree. So let's go ahead and draw. Is there a way to access all my codes in the files section in Canvas? All right, so top of the tree is the root. And we'll often use arrowed connectors to get to our children. If a node has children, which they may or may not. All right, and here we have our first tree. This is going to be a whole bunch of terminology that's going to go along with this. So let me go ahead and label my nodes so that we can refer to them. All right, so we have the root. It's going to be a named node or a specific index in the array. That is where the rest of the tree can be reached from. It is depicted If I can type that correctly, that's way off. Depict. Let's see, where's my eye supposed to be? There it is. At the top. Child. A node can have 0 or more children. Nodes that share the same parent are known as siblings. So A, B, and C are siblings of each other. All right. Ancestors, nodes that linked their way to us. So the ancestors of node D are A and the root. This example, only node that would not have any ancestors is the root. A leaf node is going to be a node with no children. Internal versus external nodes. Leaves are external. Others are internal. Yes. A is a parent, and your parent is your first generation ancestor, one generation away. Your grandparent is an ancestor, and then the generations away, right? Great grandparent. It's the same terminology. Only difference here: the human pet have 2 parents, but with a tree data structure, you're just a single parent. Levels. Yeah, let's see, height. A tree has a height based on the number, or let's see, based upon the distance from the root to the lowest leaf. Note, there are 2 systems here. The convention we're using, the tree above, the height is 2. Okay. Other systems, and the other system, the height is 3. So the root A and C, so let's see. So let's go ahead and say A and C, and then everyone else is a leaf, B, E, F, G, H. B, D, G, and H. All right, so just like a regular tree, if we're actually looking above ground, the branches are part of the internal structure of the tree, whereas the green leaves are leaves, right? Once you get to an actual leaf on a tree, there's nothing that goes beyond the leaf but space. Tree levels. All nodes at a given distance from the root comprise in the tree. The example tree has 3 levels. right? Some systems will label that as level 0 through 2, and the other system as levels 1 through 3. Either way, there are 3 levels. It's the same. Yeah, so internal has children, external does not. Yeah, so external nodes and leaf nodes are the same. Right, so you can say leaf nodes and non-leaf nodes. So it's just two sets of terminology to represent the same portion of the tree. Node depth, not to be confused with tree height, is how far away the node is from the root. Right, so the root has a depth of 0. A, B, and C have, sorry, 1 second. A, B, and C have a depth of 1. And the others are at a depth of 2. All right, so the depth of a node would be the same as the, no. Right, so the depth of the node would be the same as the level of the tree. All right, so level 0, root, who has a depth of 0. All right, so we try, of the conventions that are available in trees, we try to go with conventions that line up with each other, because it's 0 away from itself. Just like how far is the first element of the array from the base address? It's 0 away. You're already there. Right, so if you're at home, how far away from home are you? You're a 0 distance away from home because you're already at your destination. All right, 1, all nodes with the depth of 1, level 2, all nodes with the depth 2, level X, all nodes with a depth of X. Let's see. Let's see, find related sections, 'cause we're not quite to binary trees yet. Oops, if I type it correctly. Tree data structures. R. Right, so there's a fair amount of terminology. So you see an example here in Wikipedia. 2 is the root. 7 and 5 are its children. 7 has these children, and so on and so forth. So we have 4, 1, 2, 3, 4, 5 leaves in this particular tree. And those that aren't leaves are our internal nodes. Right. This is a because when he talks about this being a directed acyclic graph as well. When we get to this as a link-based structure, we'll mention that again. It's not what I meant to click. Come on, Google. It's always annoying when you're faster than the computer. Of course, it's always annoying when the computer's too slow. Yes, yes, the computer, which means the same thing as saying the computer's too slow. All right. Tree airiness. Airiness. The airiness of a tree is a structural rule saying how many children any given node of the tree will support. All right, so for example, a 4-airy tree allow as many as 4 children per node. So here's some example trees. 4-airy trees. And that is a triangle. I don't want a triangle. Circle. And we'll just add a few circles in here just because. We want there to be lots of circles. And we'll throw a smattering of other ones in here, doesn't much matter. So the root has 3 children. Second node from the second level has 4, which is what's getting us to our 4 space. And then the other nodes have however many children they have. All right, so this key node here is driving the airiness of the whole structure of the tree. Yeah, so the height of this tree is 1, 2, 3, 4. So our longest path. So we want to look at the height of this tree. Look at one of the paths that takes us to the lowest level, and there are 4 hops. All right, so I could just take that little subsection, and that is a 4-airy tree. And I could just grow from that tree. And they will all be 4-airy. Right, example 3-airy trees. Not array, airy. Get autocorrect getting me here probably. And let's go ahead and kill that child there. That there, that there, that there, and now it's just 3-airy structure. I got detached. And then we'll get down to 2-airy, which is also known as binary. And there's going to be a number of nodes. Example is going to be getting us to the 2-airy state. All right, that one, all of those are at the max. All right, so what does this matter for? The airiness of the tree of the tree is going to drive actual code structure. All right, so if we're going link based, have a 4 node, it's called node 4, whatever, class node 4. And it's going to have its data section. And what's going to have is an array. Node 4, node 4 links type situation. So we can have 4 pointers per node in the structure. All right, if we want to have a node 3, our data node 3 link, we have links 3. Okay. The maximum airiness just depends on the tree that we want to represent. Right, so if we don't know ahead of time, node n, right here we have to have a node n star children type thing where it's dynamically allocated. Right, so we can certainly support programmatically a tree of any airiness, right? 17 kids, right? It's possible someone has 17 kids. So that relationship, you have a collection of children that's 17, or you might have someone has no children. Right, so it depends on the data that you want to model, what's going to be appropriate. One of the places that we're going to use trees in actual application space will be the databases. Right, so databases use indexes to store data, and they're going to be using B trees, which we'll get to store that data. And that's B trees are, the airiness of B trees are quite significant. And that SQL Server at least bases it based off the page size, how many records you get to in a page size and stuff. So you might have 100 or 200 children in any given node. So some flexibility is going to be needed there to support those particular operations. Array-based. All right, so with array-based trees, the root is at index 0, and then children are calculated as an offset from their parent based upon the parent's index. All right, so we have the root at 0. So if we have a 4 array, child 1 is going to be at 4 times 0 plus 1. And then each children will be the same idea, 4 times base plus an additional offset, 3, 4. 2 array, same idea, roots at 0, child, let's see, I got some copy paste to take care of there. Child 1 is going to be 2 times plus 1, and same pattern as above, except we only need to go 2 away. All right, so if we're at index Yes, you couldn't write a general tree program where you pass in, where you might want to ask, you might have two options, or you might ask what the arrayness is going to be at runtime, and we use the node end style. We just say new, and we say they want a 4 array tree. Fine. No, the constructor says children equals new array 4 type thing at the point in time. Well, we don't want to do that constructor. Yeah, no, it's just as needed. Lazy load probably be a better push there. Yes, we can definitely do it. All problems are solvable. Question is whether or not we like the solution to the problem for our computer. All right, so if we're at index 3 in a tree, left child is at 7 and right child is at 8 type thing. So let's show you this is array real quick. Index 0, 1, 2, etc. Data. So if we have the root, that is 5. And let me draw a tree, and then we'll just show it both ways. That should be big enough. And we have some arbitrary values, 5, 8, 2, 9, whatever. All right, so 5 is a root, 5 is at index 0. It's left child, child 1. It's 2 times 0 plus 1 gives us a 1. That's where 8 is. And then 2 times 0 plus 2 is our 2. That's where 2 is. And let me change the values. In fact, let me change it to letters. That way we can keep our indexes and names different. Let's call that F, J, B, and whatever, K. All right, so F's the root. J and B are its children. J has no children. J would be at 2 times 1 plus 1. All right, 2 times 1 is 2 plus 1 is 3. So this would be left of J and right of J. B is at index 2. 2 times 2 plus 1 is 5. We have K. And then there are no other children. All right, so both of these link based. All right, so when we're drawing it out like this, you could presume this is a link based implementation. This is a node pointer, and we have a couple pointers pointing where the children are, wherever they happen to be in memory. And here's the same tree as an array-based implementation. The root is the first value. The next 2 is the next level. The next 4 after that is the next level after that. The next 8 will be again the level below K. And then 16, 32, doubling, right? Because each level can have twice as many nodes as the level above it with a binary tree. Whatever the n is in the arrayness, have that many times level. So if it's a 3 array tree, where you have 1, 3, 9, 27, 81 nodes that can exist in each level of that tree. Go over what again, Mohammed? I didn't see a first question. The index, right? So the index, so we have an array. Array just could be simple integer values or character values like we have here. These could even be nodes if we wanted them to, but whatever the data type is, this would typically be the data type, right? For templating, just T. whatever the template type is of the nodes. In the relationship of the tree, which is like what the lab is going to be. It's an array-based tree, and we're just going to be filling things level by level. Right? In fact, that's do the levels. Level 0, 1, 2, 3. Yes, we still have to give it the empty space, because if we were to add a child, if J picks up L as a left child, L would go in index 3, or if J were to pick up a right child, L would go to index 4. So spaces or sparseness in the array is the typical reason why most arrays are not going to be, most trees are not going to be array based. Right? Trees are more commonly going to be linked in nature, but there are, when we get to tree structures, which will be array based for a couple of reasons. It does not like we have here in this particular binary tree example. Yes, well, that's the fundamental problem with arrays, right? Arrays tend to be oversized and waste memory. So even if we create an array, okay, we want a tree and say it's a tree that's big enough to hold 100 elements, and we add 4 elements to the tree. It doesn't even matter where they are in the tree. As an array based, it's going to be wasting space. The fact that there's sequence gaps doesn't change a whole lot. There's gonna be a lot of space that's gonna be wasted in the tree. And it's one of the drawbacks of using arrays. Right? Link based, as data is added in, we go ahead and allocate nodes as we go. How do you get B index 2 and K index? All right, so 2, so left child, 2 times parent index plus 1. All right, so this is the formula for calculating where they are. So the question, since there's no maximum number of children one parent can have, right? So that would be the areaness. So if you wanted to, if we're defining a 4-array tree, then the code needs to work as such. So we need a code such that we have a value 4 here that we're going to use to multiply by the current node's index to get to its 4 children. All right, so you just get add a field, a member field saying areaness, it's array. And right, so if we're doing a generic array-based tree code base, they have to construct it with the areaness of the tree. So they can say 2, 3, 4, X. We set that as X. And then if we want to get to a particular element to branch through, we have to do the calculation where we do that multiplication. And then we can get to any child from 1 through that value. So we can do it. It's just usually this values would be, we look at some 2-3 code, and we'll see this because how it gets there, all that fun stuff. Yes, we have to know ahead of time, otherwise we wouldn't know how to navigate through the array. This mean index of node, right? So F is a node in the tree. It's the root, so it has index 0. To calculate its children, we take that 0, we plug it in. 2 times 0 plus 1 gives us the left child. 2 times 0 plus 2 gives us the right child. So if we're in the tree at a particular point in time right now, and we're in node B. We're presently at index 2 in the tree. 2 times 2 is 4, plus 1 is 5. That's where K is. And then 2 times 2 plus 2 is 6. And there's no right child. Left child is at 7, right child is at 8. Let me see. So yeah, that was just an example when the index was 3. Where did I have that? Right, so here, plugging this 3 in, 3 times 2, 6 plus 1 is 7. Let me add index. All right, so index, right, index of node into array is 3, index 7, the right child is at index 8. Chloe, that's for a binary search tree. Right now, we're just talking about trees in general. And this particular tree being a two-array tree. A binary search tree will be a two-array tree, which we'll get to. That particular binary search tree is a tree that specifies both the arrayness as well as an order within inside the data. Okay, let's swing over to the labs because people have been asking about labs. All right, so binary tree lab. It literally is as simple as exactly what is in the lab description. All right, people want to try to turn this into link-based semantics or try to put order-based semantics in there, but we're not yet at any of those semantics in our trees just yet. So you'll create your tree class has 2 members, the array, which stores the data of the tree, and a count, which indicates how many elements have been added to the tree or how many data points have been added into the array. An add function literally takes it and adds it to the count and then increases the count. So the first value that you add goes to the root, whether it's 10, 20, 100, whatever, that's the root value. The next value, we've already incremented the count from 0 to 1 because there's 1 in here. So we add it again. It's at index 1. So it will 55 or 5 million. And whatever the root is, it doesn't matter. We're filling level by level. First value goes index 1, second value goes index 2, or excuse me, we rewind. First value index 0, second value index 1, third value index 2. It's a straight level by level fill. So if you populate the tree, the values 1, 2, 3, 4, 5. That's exactly what you'll see in the array, 1, 2, 3, 4, 5. And then we're going to go do a traversal from that, which we are going to go ahead and get to it right now. Let's see, yeah. So traversals. No, a two-array tree is a binary tree. By like bicycle, it means 2. Or like binary, 0 or 1. There are 2 possible. 3, 2. Okay, 3 to 2. Traversals. All right, so traversing just a simple array being a linear data structure, we can go from the first element to the last element. Traversing a tree is a different story. All right, so first off, we'll look at traversing binary trees. With these traversals, we presume a left to right resolution order that is also arbitrary. So let's go ahead and do a drawing of a tree, and then we can traverse it. And we'll give it some arbitrary values. Some fun lag. Let's see. Make sure I get all our good angles here. That looks like it's probably gonna be enough. And this goes over there. Okay. Line things up a little bit better. Good enough. Okay, so we will, oops, just arbitrarily label these A, B, C, D, E, F, G, and H. Okay, let's try to get a better white space management here. All right, so when traversing, we'll start at the root. There are 3 patterns that we can apply. There is a pre-order traversal, in-order traversal, and post-order traversal. Pre-order. What we're going to do is we're going to visit the node, which means looking at the data. Then we'll go ahead and traverse left. Let's do stashes. Traverse left and traverse right. And this is a recursive pattern. So starting at A, right? A, the root, is the first node. From A, let's get some annotations here. All right, so we start off at A and we spit it out. Then we're going to go and go left. Yeah, we can do that later. All right, so from A, we go left to B. First thing we do is we're going to visit the data and look at B. All right, we'll spit it out at the end here. I'll retype this later. We go left. There's no left subtree. So we come back to B. And then we go ahead and go right. Takes us to D. Left from D takes us to G. Go to left subtree of G, which is empty, so we come back. Right subtree of G, that's empty, so we go back. Right, so we've now completely finished processing the G node. We did step 1, we visited. We did step 2, we traversed left. We did step 3, we traversed right. That means we go back to whoever called us. And now we're back to D, go and traverse right. And done the same thing there. We processed the data of D. We went to its left subtree, completed that left subtree, and went to its right empty subtree, which means we now go back to B and the same pattern back to A, right? So now that we're back to the root A, we've completely processed A's left subtree for the values B, D, and G. So now we can go and go right to C. Nope, not going by levels. what we're going to be doing is a large rubber band or a vacuum seal. We're creating a path. Let's try that again. Creating a path all the way around the tree. All right, so C has been spit out, so we'll go ahead and go to E. Empty left subtree, go to H. Empty subtrees, just back up, on F, so it's been generated, back up and back to the root, and then we're done. Okay, so just F, C, 1, 2, 3, 4, 5, 6, 7, 3, I'm missing something here. Let's see. Who did I write? A, B, D, G, C, E. Okay. All right, so let's do this again for a tree like it will be in the lab. Create a few nodes again. That seems like enough. Okay, lag. Root is 1. Its children are 2 and 3, and then 4, 5, 6, 7 for the last level. All right, so we'll go and do a pre-order here. Go to 1. And go to 2. Go to 4. And 4 subtrees completed. Back to 2. Come back. Go down to 5. 5 is completed. Back up to 2. Goes back up to the root. Now we go down the right-hand side. And there's nodes. So when you're doing the lab per traversal, this is the output you should expect to see for a tree that looks like this. 7-element tree. In order traversal. It's the same 3 steps, except we move the visit to in between. Let's see how to restart the numbering here. Well, I guess we just turn it off. And then we'll turn it on, see what happens. There we go. All right, so start at the root. It says traverse left. So there's the left subtree, so we'll go left. We're at 2. It says go left. So we'll go ahead and go left. Takes us to 4. 4 says to go left. There is no left. So we come back. And now we can visit. So our first output is going to be 4. Now we've finished the second step at node 4. We can traverse right. Back up. And then work our way. So now we're back to the 2 node. No, these I'll get to your questions in a second after we finish the traversal. So we're back up to 2. 2, we've finished the traverse lefts. Now we can go ahead and output and then go right. 5 has no left, so we can spit it out, come back to 2. And we've now finished the left subtree of 1. So we finished the traverse left. So we go ahead and visit the node, spit out the 1, and now it says to go right. And keep on going until we finish left subtree, and then we can spit out data, come to 3, goes on over to 7, spit it out, and then back up to the root. Okay. So this question, what's the condition for using an if statement? I assume that to see if there is no left subtree. So if this is a linked base tree, if the left pointer is null, there's no left subtree. If the right pointer is null, there's no right subtree. So you'll know that your base case for the recursion is when you run into a null pointer. I'm not quite following the question. The numbers before were deleted. What do you mean the numbers before were deleted? Oh, I mean the scribbles? Yeah, the scribbles. I mean, I put the answer. Oops. The value of the scribbles are here. And then the drawing itself would be in the video. If you want, I can take a screenshot of that if you want as well. In order, put the output 2, 5, 1, 3, and 7. And nope, let's go ahead. Trying to get the back where it was. All right, so the arrows, whichever traversal we're going to be doing, this arrow pattern is going to be the same. We're going to be going from a node to its left child, from a node to its left child, from a node to its left child until we're have no left child to go to. In the same pattern, coming back up and then going right, coming back up, going right. The only difference between the in order, pre-order, and then the post order is when we look at the data. So if we do a post order, right, I could effectively just copy this image and then drop it down here again. The difference is going to be when we output. All right, so let me get the steps. That just does not copy well at all. All right, so with the post order, we are going to basically go to our first leaf. So we go left, go to 2, 2 has a left, so we go left. 4 does not have a left, so there's nowhere to go. 4 does not have a right, so there's nowhere to go. So we found our first leaf and we can spit it out. The lab is arrays. So the base case for the lab is when the index that you're at is no longer within the bounds of the tree. So it's 3 elements in the tree. Your count is 3. So to index 3, that's outside of the tree part of the array. All right, because 0, 1, and 2 are the 3 elements in the tree. So the count is what you use for the base case. Okay, so 4 has been processed. Go back up to 2. 2 is not a leaf. So go to 5. 5 has no Trojan, so it's a leaf. So we can go ahead and process it. 4 and 5 are both processed, so 2 is logically a leaf at this point because it no longer has any unprocessed children. So when we come back up from 5 to 2, go ahead and spit it out, and that brings us back to 1. 1 has the right subtrees, 3 has a left subtree, 6 is a leaf. So we go ahead and spit out 6. 6 takes us back to 3. 3 still has children. 7 is a leaf. So we spit out 7. 7 takes us to 3. And then 3 takes us back to the root, and then we're done. All right, so that's all there is to the traversals. That's for the lab. The base case is to check the count. Count lets you know if you're still inside the data portion of the array, which is the tree portion, or if you're falling out. Okay, let's go ahead and take 5 minutes. Yes, the lab is array based. And you can use a fixed size. I don't care how big, whatever. We already went over static versus dynamic based arrays. So you want to make it a 50, a 100, a 2000, a 12, doesn't matter. Okay, so there's a question about when you decide when to use a post order, in order, or pre-order. We haven't quite got to that yet, but certain tree structures a given traversal may have meaningful information. Usually pre-order is going to be what's used often because you go to a node and then you look at it and then you decide, do you want to keep looking, or are you going to go left, or are you going to go right, or are you going to do all of them? So at the moment, it's just a basic pattern, but as we get to binary search tree, we'll see that an in-order traversal is useful there, and an expression tree is a post-order traversal has some meaningful information that we can take a look at. Okay. Ordered trees. It's just going to be a tree structure where the values, the data elements are going to be considered in the construction of the tree. Order could be of the left, right, pattern, or up, down pattern. So let's get a dash over here. All right, so binary search tree. This is going to be an ordered tree. It's a binary search. It's a binary tree. And the order is left to right. Values lower than the root belong in that root's left subtree. Values greater than the root belong in its right subtree. Duplicate values are going to be rejected or have special handling. So constructing BST is as follows. Starting at the root, add a value. If the root is empty, the first value added becomes the root. If the root is non-empty, compare the value being added to the root. If the value is lower, add to the left subtree. Otherwise, add to the right subtree. Okay, so let's build a tree. We'll go ahead and add 44, 22, 15, 78, 100, 64, and 9. Seems good. All right, let's see. Let's get a node big enough to handle. And not like 100 anymore. Let's make it 97. Okay. All right, so initially our tree is empty. So the first data point that is added comes the root. Now we have a tree and we want to add 22. 22 is less than 44. So we'll go ahead and link it in. Left subtree of 44. Since left subtree of 44 was non-existent, we just go ahead and create that node as a leaf and link to it. Next up, we're adding 15. 15 comes to the tree. The root has a value. It's less than, so we'll go left. Left subtree, the root of the left subtree has a value. It's 22. And 15 is less, so we'll go left. And since there's no left subtree off of 22, go ahead and create the 15 node and then link it over there. Next, we have 78 coming along. 78 is greater than 44. Right subtree 44 is empty. So we add it in. Again, next up we have 97, greater than 44, greater than 78. So go ahead and drop that to the right of 98 since there is a space available for 97 here. 64 comes along. Start at the root again. 64 is greater than 44, so we go right. It's less than 78, we go left. Left subtree of 78 is empty. So go ahead and add 64 there. And then we have 9 coming along. Let's see if I can squish this out a little bit. Not quite. All right, so we're adding in, I believe it was 9 or 6, whichever it was. Start at the root. It's less than. Go left. Still less than. Still less than. So it goes to the left. And we link it in. All right. So a subtree. A subtree is a tree that has the same characteristics as the parent tree. All right, so this entire tree is a binary search tree. This left subtree of 44 is also a binary search tree. All right, same thing, the right-hand side of 44. This is a binary search tree. Or if we look at the values, 78 is the root of the subtree. Values that are less than it are on the left. Values that are greater than it are on the right. Same thing if we look at this binary search tree, 22. Values lower than 22 are in its left subtree, 15 and 9. And the same thing applies here. 15 subtree is a binary search tree. Left subtree of 15 is values lower than 50. This is the only way to order a binary search tree. All right, so adding that search to the definition of this tree is what means this is the only possible tree that you could get being presented with this data in this order. There is no other possible binary search tree to get built from this set of data in this order. So circling back, in order traversal. All right, we'll do the full steps. So we start the root. All right, that's 44. And then go left. All right, so we're at 22. Go left. At 15. Go left. At 9. Go left. All right, so no 9 left subtree is completed. Output 9. 9, go right. Back to 15. 15, left subtree is completed. Go and output 15. 15, go right. All right, our subtree is done. 15, go back to 22. 22, left subtree is completed. Output 22. All right, so we're at 22. Go back to 44. 44, left subtree is completed. Output 44. 44, go right to 78. 78, go left to 64. Numbers. 64, go left. Where? 64, left subtree. 64, left subtree completed. Output 64. 64, go right. Where? And 64 goes back to 78. 78, subtree is completed. Output 78. 78, go right to, we have 70, 97. 97. 97, go left. Nowhere. So 97, left subtree is completed. Output 97. 97, go right. There. 7 goes back, same difference. To 78, and 78 goes back to 44. And all done. All right, so if we look at our output, final output, 9, 15, 22, 44, 64, 78, and 97. Did I miss anybody? 3, 7 nodes. We got there 1, 3, 7 nodes. All right, and so you'll notice this is nice and sorted order. So an in-order reversal is quite meaningful if you have a binary search tree, if you want to produce a sorted list or sorted output from a binary search tree, you can. And one of the things you might want to do, just a generic binary search tree, is rebalance it. So having a sorted list makes it easy to build a binary search tree, because what you would do is you would actually produce a sorted list and you'd grab the middle value, because the median is a great divider, because all the values to the left are lower and all the values to the right are greater. So it makes for a good root. And then you do the same thing over here. 15 is the median there. That makes a good root of 9 and 22. And you can produce a fairly balanced binary search tree from a sorted set of data by applying a special processing order. Questions on building a binary search tree?
Will we get to the code for that at any point?
Yes. Yeah, okay, I'll get to duplicates in a second. So using the binary search tree, we use it to search. And the search is much like build operation, except we'll just look for the data. We'll start the root. Data is a match. Turn the root data Otherwise, if search value is lower, traverse left, or if higher, traverse right. All right, so if we get to an empty subtree in the data, it's not found. All right, let's go ahead and build a binary search tree. We'll start with 50, 25, 75, add 50 in there again, 49 and 51. All right, so our first 50 comes the root. $25 comes along, and we'll build that off to the left since it's lower than 50. $75 comes along, goes off to the right since 75 is greater than 50. And now we have 50 again. So where do we want to put 50? It's somewhat arbitrary if we want to keep the extra values to the left or to the right. So we'll go ahead and put 50 on left. All right, so I'll put question 50 here. And we decide to toss it to the left. So we have the 50 node. 50 is greater than 25, so it goes to the right subtree 25. All right, 49 comes along. It's lower than 50. Greater than 25, lower than 50. So it's down further in the tree over here. And then 51 comes along. Greater than 50, lower than 75. So it comes down to our subtree over here. All right, let's generic subtrees. Did you see a triangle that represents a possibly empty subtree? So get some space here. All right. So these are subtrees that we might be able to grow into. All right, so assuming integral values. If I want to add a value to this existing binary, what range of values or sample values might I add such that it ends up in this far left triangle? All right, less than 25. So if we want to add, yeah, so less than 25. So if we want to add 5, -5, -100, that's less than 50, it's less than 25, it comes in this left subtree. Now, this second subtree, what range of values? Let's go to the other side. So on the mirror, far right subtree, what range of values would go in this subtree? Okay. Right idea, wrong operator, but greater than 75. Right, all values greater than 75 end up in this subtree somewhere, 100, 200, 150, 76, all in that subtree. And let's start working our way left. Now in this highlighted subtree, yeah, we got your intent, right? Greater than 51, that's part of it. Greater than 51. Additionally, it also has to be lower than 75. So I'm going to change my operation here and do a different notation. Square notation 51 to 74. And see if I can make this a little bit wider. That's not bad. All right, so, and let's make it sit. I got square brackets. So any value from, assuming whole numbers, if 52 to 74 comes in the tree at this point in time, greater than 50, greater than, less than 75, greater than 51, right? So the parent and grandparent establish the bounds of the values that can exist in this subtree. All right, so this subtree, nothing, because we have an extreme value here. There are no values that can get in here because it has to be. And actually, I need to restate. I said parent and grandparent, the first parent on the right-hand side and the first parent on the left-hand side specify the bounds that can fit into a subtree. All right, so the first one to the left and then the first one to the right, just looking at the angles. The bounds over here, 50. First parent on the left is a 50, first parent on the right is a 50. So this subtree is also dead because of the, this one's because of the duplicates. Right, this one's also dead because the value ranges does not allow any extra values in here unless we want to consider 49. For our duplicates would fit there. And first to the right, first to the left is 25. So we got our range 26 and 48. Right, so duplicate values are going to immediately cause subbranches to effectively not be able to grow with the exception of additional duplicates. So the duplicate values are much problematic to the data structure because it's causing dead branches to form. So we want to avoid that. So alternatives, right? So the duplicates guarantee dead branches. Branches which could only have the duplicates in it. So alternatively, if we want to allow duplicates, right? Say our data set is colored books. So we have blue books, red books, green books, etc. For whatever reason, we decided to key off of the color. Right, so we might have several blues. We have what? A Stephen King blue book, an Anne Rice blue book, and a Dr. Seuss blue book. So we want to go ahead and have all our blue books on that blue bookshelf, whatever type thing. So I mean, we just add in, could add in a linked list, for example, inside the node structure to allow for duplicates. And that list grows and has minimal impact to the structure. Just have a little bit extra overhead by having an extra point in each node. So all the nodes don't have duplicates, just have a null pointer. There's space cost to it. But if the data that we want to wants to be arranged like that, then we can solve a problem. Okay. Yeah, so the common implementation is not allowed, is to not allow duplicates because if we say we have 49, we have 49, right? It's secondary data that can differentiate right? So if we want to allow this key value 49, 49 represents classroom 1. And 49 also represents classroom 7, because both classroom 1 and both have a seating capacity of 49. Right, so if we're building a tree of classrooms where a capacity is the key data, and more than one room can have the same capacity, then we need to allow for it. But usually, if we're creating a tree of classrooms, it's be classroom numbers. Right? Classroom 1, 2, 3, 4, 5, and then it has, oh no, how many seats does classroom 5 have? I search for classroom 5 in the tree, and it comes back and says there's 9 seats available in classroom 5, or whatever it may be. But if there is a use case, I want to see all of the classrooms that have 49 seats, and we're keyed off the names, then we're down to a traversal. We do a pre-order traversal every time we just look at every single node in the tree, and if it matches 49, we just say here's the classroom information type thing. Yeah, so you can decide to support duplicates if you want to or not. In general, we don't do duplicates in our binary search trees because it's a problem. But if there's a problem, one can find a solution. And the solution that you might want to use may well depend on what the application business case is. Okay, did I miss any questions? I think I got all the questions. Okay. Deleting from a binary search tree. All right, so there are 3 different cases that may apply when deleting. First is deleting a leaf node. Second is deleting a node with 1 child. And the third is deleting a node with 2 children. All right, so case 1, deleting a leaf. Just remove the node and null out pointer of the parent that was pointing to it. Case 2, deleting a single is not too hard. We're going to bridge the node. The grandparent will point to the child of the node that we're deleting. And we'll then delete specified node. Case 3, what we want to do is we're going to use a delete by copy mechanism. That moves a value from lower in the tree into the node that we want to delete, and instead delete the source node value. What we're trying to do is create a case 1 or case 2 scenario, which is simpler of a structure change. All right, otherwise, if we delete an internal node that has 2 children, if we're just to delete that node, we would now have 3 branches of the tree, the main tree and 2 subtrees that we just pulled off or pruned off the tree that was in the parent node that we were deleting. We could just do some reattaching, splice those branches back together, but the tree structure gets pretty grotesque looking, so not going to do that. So let's show some examples here. Right, deleting a leaf. Right, pretty trivial. If we want to delete this node, set that was no longer there. Right, so we want to do it in 2 steps. We kill the node and pull the pointer, and we're done. Pull the pointer and kill the node as long as we end the node's removed. Right, and we could have done the same. There we go. With our one other leaf, instead, what is? I don't know what the normal color is. If instead we wanted to delete this leaf, delete the node, null the pointer, and we have a good old binary search tree. Everything should be good to go. All right. Now let's delete a node that has a child. And we'll add data points in here so we can make sure that the data relationships make sense. We'll make the root arbitrarily 19, left children are 8 and 40. 40 has a left child of 35, 35 has a left child of 28, and 5 is right is 37. So what we want to do is delete 40. He has a single child. So what we want to do, right, the parent, which is the grandparent of 35, we want to go ahead and point on over to its grandchild. And then we can go ahead and get rid of the 40 node, which includes its link. And I'll just move this up to make it look a little bit better. All right, so let's double check. The 35 subtree, its values are 28, 35, and 37, all of which are values that are greater than 19. All right, so double checking this binary search tree, act a binary search tree, all the values are in their appropriate location. And we're good to go. All right. Let's see. I forgot to do some labeling. Oh, we got case 1. Now we have case 2. And now we can roll into case 3. Let's make the tree a little bit bigger. Add in some children for nodes. Let's see. 25 and 48. So a question, let me see what that was. So a binary search tree is going to be a doubly linked list. Yeah, so it's going to have the same node structure as a doubly linked list node. So a doubly linked list node next and previous is a commonly named or common named 2 pointers. For a binary search tree, we're just going to call them left and right. So we could take the exact same DLL node structure, copy it, and then rename the pointers, and now we have a binary search tree node or binary tree node, whichever we want to use. Okay. It's all right. So we are creating a hole here at 35. Right. Break this node out. Right, we do something similar. 19 now, X to 28, and then 37 gets reattached in here. That'll work, but it tends to unbalance our tree. It makes it lean one way or the other. And as much as possible, we like our trees to be as triangular as possible. Well, to achieve our ideal notations of log time, when our trees are actually mathematically triangular based off of some rules we'll get to later. Delete. We're going to one or both of these subtrees for a candidate value that can replace the hole we just created. Each of these subtrees may have one value that will work as a candidate. Right? Looking at the left subtree. If 28's going to this bubble, right? This bubble is going to stay where it is, and we're going to put a new value in our orange circle. Which of these two values would work and still be a good parent to the remaining values in this subtree? 25 or 28? Right? 28. So if we move 28 over, having 25 in its left subtree would still be good, right? And then the hole is in this position. Right, so that is one way we could do it, where we take the rightmost value from the left subtree, copy it over, and delete that node. So we'll do that one and we'll finish it up. So let's got that. All right, so now we're into deleting this node and single node situation. So single node situation means all we have to do is bridge over from the grandparent to the grandchild. Which means we can delete that node, delete the old pointer, and up just because. Yeah, so it was pointing to a node whose value we didn't care about anymore. So the node's still there. So we'd say 28 to left equals the node to the left pointer as it was, it has a left child. Got right child, we have pointed to its right child. And here we got case 3, alternative. Where we do the mirror, we'll take the leftmost value from the right subtree. All right, so instead of pulling 28 out, we pull 37 out. And then delete that node. Copying over as we did before. Parent, the grandparent points to the child, points over there. And then we can do some housekeeping and clean up unneeded memory. And bring it up just for making it look nicer. All right, so let's do that again. Case 3, example 2. And generic form. So put 37 back in there, get some reset, fix my link. All right, and now we'll do some fun triangles. To represent data that could be there. And we'll just label the triangle. We don't need to put the ranges. We know how to get the ranges. Looks good. Let's see. If we want to delete the root, yeah, we can delete the root. Which do okay. Well, so we'll do that scenario in a minute. And we're going to be pulling leftmost and the right subtree. Okay. So let's not put that there. Let's add, just have 4 trees at this level. And exist. Okay. And I forget what value, but the value that was in there, we're going to delete and say that there's a 35 here. And move these triangles around. Okay. And we'll call this subtree W, X, and Y. All right, so we've decided to take the leftmost value from the right subtree. All right, so the orange node is the node we're deleting. So whatever was there, 33, 29, 31, whatever it was, we want to take the leftmost value. So the leftmost value means we start off in the right subtree and we just traverse left, 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 left until there is no more left. So we get to a null left pointer. So that means there cannot be a subtree over here, which makes this the leftmost value in the right subtree. If there was a 34, 33, 32, 31, right, then there would be a subtree over here, V, and then we would be pulling those values. So this is the leftmost value, and we're going to go ahead and copy it in. All right, so the value is left there, it's over here, and now we have this delete scenario. So we're going to bridge the gap. And let me change this X. We bridge from 7 to W. And I'll point out that we copied to the delete. And here we'll just have some cleanup. Right. And the W sub tree got lifted up a little bit. Right, so whatever values that could have been in this W sub tree before should still hold the same relationship after the fact. Right? Right ancestor, left ancestor are 7. So the range of values that can be in the sub, assuming a whole number of values. If we go back, look at the original state of the tree, left ancestor, right ancestor, 35 and 37. So in the subtree, still 36. So the binary search tree is still in a valid state. Code, it's a binary search tree. All right, so example 3. Deleting from the root, assuming 2 children. It's the same, it's a 2-node delete pattern, except there are more that were there. So we want to make sure that things get put back in the right place. Right, because we're reattaching to a larger tree. We want to make sure that that larger tree is still all present and accounted for. Let's see, is there a reset color? Is it that one? There it is. Okay. So delete the root. All right, so you choose either the leftmost value from the right, excuse me, the rightmost value from the tree, which is 8, the value from the tree is 25. Now, we can arbitrarily just default to one subtree over the other, default subtree. To if we keep in the left subtrees are going to get a little bit sparse here. We want our tree to be as full and lush as possible. We want to see lots of green, much twiggy steps on there. So one of the things we might do, look at the heights of the subtrees, then pull from taller subtrees. So the right subtree is only taller. So when we go ahead and do the leftmost from the right subtree, go through the step. Subtrees in here. Goes around a little bit. So 19 goes away and 25 copies in. Since this is the trivial example, we switched over to a delete by leaf. There's not a whole lot to do. But right, it's still just a delete by copy. Yeah. And we just go and pull out this 25 node and we're done. We deleted it from the root. So the root is just another node. If root is the only tree, then we're doing, and the tree do need the root to null. So we do have an edge case there from going from a 1 node an empty tree. Otherwise, the root has 1 child, and we need a bridge. Right? Bridging to nothing just means that 1 child becomes the root, right? So if simple delete root, there's 1 child. Wait for Google. All right, so if we have this situation and we want to delete the root, 35 to the tree. All right, find our root. Second, okay. Away from a file, so section. Man, is it just my computer? Wow, that's terrible. Okay. All right, trees section. And binary trees code. So let's go ahead, take a 5-minute break. All we're going to do after this point is just look at the code. So we're more or less in the lab time. So we're just going to look at the code. Oh, wait, before we take a break, I meant to look at test one. Test one. Questions 18 and 19. Waiting. All right, or 17, 18. Okay, so find second. All right. Intercurrence equals 0. Several ways you can do this. More or less, we just need to count or use the flag since we only need the second one. For loop that goes from the beginning, the size. All right, if number sub I is equal to the 4, and we found a match. And it's equal to 2. Return back and we're done. And if turn back -1 indicate fail to find a second occurrence of that key. Some of you bugs here where you weren't actually returning the value, which was before. So forgot your test case, but I didn't actually say to put the negative test case, so not a big deal. Some of you found the occurrence, so that was not what the algorithm was asking for, so that was partial. You wanted to find test occurrence, which is not what the question was asking for. That was partial credit. Otherwise, it's just a loop part. That's probably speed test was not impressive. Yeah, my internet is in a less than ideal state at the moment. I'll reset the network on the break. So going back to the test. So restating, right? Just a loop for the most part. Logic that looks for matches, and then once we get to a threshold, we return back that occurrence of match, right? We could generalize this, change the function to say find nth occurrence type thing and add in n, and when the occurrence equals n, in this we could find the third, the fourth, the fifth, whatever. All right, DQ. DQ is supposed to return back data. Some of you are not returning back data. Some of you did not account for the list being empty. So you would have lost the point for that. However you want to being empty. Otherwise, data is equal to the first. Data. What's my doing? Node star temp is first. So we can clean up the memory. Was first. Next of you were not using the naming first. We'll like lost half point by calling it something that doesn't actually exist. And we can delete temp and return the data. But yeah, that's the key operation equals next. Making sure that there's actually something to DQ. Yeah, I was a little bit, if you just print out a fine, you're supposed to return it and there's no memory leak. Okay. Now we can take 5. And then we'll just come back and look at code and any of the lab questions we might have. So just code and additional lecture notes for tonight. So I'll take 5 and I'll be right back. And talking not on mute is always a helpful thing. It's like the reset did kick me off for a little bit, but responsiveness seems better. How is the audio coming through?
Sounds good.
All right, so we've got code. Take a look at binary CPP. Right, so here's our tree nodes. It's pretty much the exact same as our double link list node. It has a data field and two name pointers of the type. Their self-referential type. Default constructor just sets everybody to 0. And then we have an overloaded constructor. We can pass along left nodes and right nodes and along with the data. Right, binary search tree. Here's our name node root. Constructor sets it to null. And then add node. All right, pass along some data wherever we add the node. This is a guaranteed operation to create a node. So that's the first thing we do. Go ahead and create the node with whatever the data was. If the tree is empty, the root's null, the root is now the new node, and we added it successfully. We're done. All right, so we do have the bool return type because detect the duplicate. And we like saying no. Say we did not add that to the tree because we don't like it. Otherwise, we get temp node, starts it off at the root, and this is just way down the tree as needed. All right, do some data comparison. If the data is lower than the current temp, which is initially the root, and the left branch is empty, go ahead and link the new node to the left branch, and we're done. Break out of the loop, return true. If the left branch is not empty, temp slides to the left. And we have the reverse looking at the right. If it's an empty right branch, we can attach. Otherwise, temp moves to the right. And if we find a data match, reject duplicates. And the tree builds up. And it just is an iterative approach. It's adding a node only involves going down a branch of the tree. We can go ahead and use an iterative approach. Some may prefer a recursive, so you can do basically the same idea recursively. So there are other versions of adding tree traversals. All right, pass in the root node to start. And if that node is not null, in order traversal, just traverse left, generate output, and then traverse right. So it's basically these 3 lines of code. If we want this to become a pre-order, just move the line up. Now it's a pre-order. If we want to become a post-order, we move it down a little bit further down, and now it's a post-order. Yeah, then fix the names. Right, this one does a right to left semantic instead of left to right, so nodes before left nodes. That's, you can do pre-order, post-order, or in-order traversal with a right to left semantic in the same way. It's just which subtree you decide to work with. Deleting, right, what we just talked about. One, find the node that we want to delete. So we're going to and do a couple of temporary pointers here. P and previous. Previous is just going to track the parent as P slides down. And we're going to go ahead and look to see where the deletion needs to be done. And then we'll call it delete by copying. All right, to delete by copying is going to look at a couple of our cases. So we're an empty right subtree. right? Because we might have an empty right subtree or an empty left subtree. If we have an empty right subtree, we can go ahead and just bridge over node equals node left. Notice the syntax here is a little bit heavy. Star and an ampersand. So we're talking about an alias. We want the actual memory address of the actual pointer itself, not a copy of the value pointer. So be careful with the syntax here. Because when we say node equals node, this effect will be persisted outside of the scope of just this function. Right, case 3, what we're going to do here, this one is not doing 11 till we're just going to go ahead and grab the left subtree. So temp equals node, and then we're going to go ahead and slide down the right branch. While the temp right is not null, track the previous, and then slide right. Keep sliding right until we're at the rightmost node of the left tree. We can go ahead and do the data copy. Bridge the gap. The previous node, which would be the grandparent, left equals left or the right. We just do a test to see if it needs to be the left or the right subtree that we're branching on. Case 1 actually already coded by these two scenarios. Right is null, node is no left, node left. If there is no left, then we're deleting a leaf and we're setting it to null. So this is actually setting the parent to null because this fun ampersand up here. Let's see. All right, here's a function that takes a, instead of just building the tree and the data that it's given us, you give it a sorted array. We jump to the middle and we go ahead and call the insert with the middle value. And then we recursively call it and call right our rebuild balance, which in turn we'll call insert to middle. So I'll just call our insert a function above, but it's going to give us a nice balanced tree because half to the left, half to the right, half to the left, half to the right is a repeating pattern because we're jumping to the middle of an already sorted array. Test old tree in the which the data. So use this approach. Code that calls the code. That's most of it. It doesn't have finding leaves, finding heights. We talk about program 2, which program 2 is binary search tree. We will dig into that one. Build balance builds a balanced binary search tree because it takes an ordered array and chooses good roots from that ordered array. All right, I think we've done more than a night. Any other questions before we call it? I did click the button to make the practice test available, so it should be available now. And let me see, that was before I did the reset. Nope, it didn't take. So let's try that again. Rest didn't work out. Okay. Guessing maybe it was already published. Let's try that. Yeah, next test. Is there, take it between now and next time? We'll go over it next time. It's got all the details of what you'll see there on the test. All right, have a good week. We'll see you on Monday.
Thank you, Professor.
Thank you.
Thanks.
Thank you, Professor.
Thank you. We'll see you next week.